Tonight, we're going to explore why humanity stopped landing on Venus. Venus should have been the planet we return to again and again. It is almost the same size as Earth, has nearly the same mass, and pulls on the human body with almost the same gravity. From a distance, it looks less like an alien world than a second version of our own. And for a while, we did keep going back. The Soviet Union sent probe after probe through the clouds, and in 1970, Venera 7 became the first spacecraft to transmit from the surface of another planet. It lasted 23 minutes. That number explains much of what happened next. At the surface, the temperature is about 467 degrees Celsius, hot enough to melt lead. The atmospheric pressure is more than 90 times Earth's, comparable to being almost a kilometer beneath the ocean. Electronics overheat. Seals and insulation fail. Pressure vessels are slowly crushed. Even the most successful Venus landers survived for only minutes or hours. We have returned to Venus with orbiters and flybys, but no spacecraft has landed there since 1985. Mars offered machines the possibility of operating for years. Venus demanded expensive spacecraft built for a world that might destroy them before a single afternoon was over. Venus was not abandoned because it was unimportant. It was quietly judged, too difficult for the amount of science each surface mission could return. By the end of tonight, you're going to understand why Earth's near twin destroys almost every machine that reaches its surface, why decades of engineering and budget decisions redirected exploration toward Mars, and why returning to Venus may be essential to understanding how a world that may once have held oceans became the hottest planet in the solar system. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. The strange part is that Venus itself is not especially difficult to reach. It comes closer to Earth than Mars does. Launch opportunities arrive regularly, and its thick atmosphere provides something Mars barely offers at all: enough air to slow a descending spacecraft. The real problem begins after the spacecraft lands. On Mars, engineers fight extreme cold by producing heat and trapping it inside the vehicle. Venus presents the opposite problem. The lander arrives cooler than everything around it, and from the moment it touches down, the planet begins forcing heat inward. Insulation can slow that process, but it cannot stop it. Cooling systems require power, pumps, radiators, and additional mass. Conventional electronics begin failing as temperatures rise. Lubricants break down. Wiring, seals, batteries, and scientific instruments all approach conditions they were never designed to survive. The pressure makes every solution heavier. The spacecraft must carry a reinforced shell strong enough to hold back an atmosphere pressing from every direction. But thicker walls add mass, and more mass makes the mission more expensive to launch, descend, and protect from heat. Soviet engineers eventually stopped designing Venus landers as machines that would continue operating. They designed them as timed experiments. Every instrument had to begin working immediately. Cameras could not wait for better light. Drills and chemical analyzers had to complete their measurements before temperatures penetrated the protective shell. The lander did not have a long mission followed by an eventual failure. Its failure was expected from the moment it arrived. Venera 13 demonstrated just how much science could be compressed into that narrowing window. It returned color photographs, analyzed the surface, and continued transmitting for close to 2 hours before Venus finally overwhelmed it. Both landers, and the ones that came between them, were built around the same blunt strategy: get down fast, take readings immediately, and squeeze out every second before the planet finished the job. Then each one died, the same as every lander that came before it. Compare that to Mars, where the rules turned out to be completely different. Opportunity was built to survive 90 Martian days. It lasted almost 15 Earth years. On Venus, you count your victories in minutes, and every mission planner after that first landing has had to redesign what success even means. What those short windows saw was enough to end the fantasy of an easy second Earth. Basalt-like rock, scattered across a low, hazy horizon. A sky the color of dirty amber, not blue, pressing down close overhead. And underneath that sky, numbers that explain everything else. Surface temperature runs about 460 to 470 degrees Celsius, close to 880 Fahrenheit, hot enough to melt lead outright, hot enough that ordinary steel starts to lose its strength. Surface pressure runs about 92 times what you feel at sea level on Earth, close to the crushing weight of standing nearly 900 meters under the ocean, almost 3,000 feet down, without a drop of water anywhere in sight. Building a machine that carries working cameras and computers through both of those forces at once, the heat and the crushing weight, sits right at the edge of what current engineering can do. Every seal, every lens, every soldered joint has to hold at once, not one after another, and there is no cooler moment to wait for. Venus's surface is not simply harsh. It is built almost deliberately to defeat the entire premise of how spacecraft get made, and that is where the accounting begins. A Venus lander needs a heavy heat shield, a hull rated for 92 bar, thick thermal insulation, and materials that shrug off acid, all of it heavy, all of it expensive, in exchange for maybe an hour or two of data from one spot on the ground. A Mars rover needs a heat shield too, but then it drives for years through cold, thin, forgiving air, stopping to examine whatever catches its cameras. It gets to tell a long story. Venus gets a countdown. Other destinations look easier by comparison too. The icy moons and the outer planets are cold and distant, but at least their electronics are not fighting off oven-like heat with every second of operation. Weighed against each other, Venus started to look like a bad investment. High risk, high cost, short life, thin payoff. That is the real reason there is no modern, high-resolution Venus rover rolling across those basalt fields and streaming its surroundings back home the way rovers on Mars do. It was never a lack of curiosity. It was arithmetic, run over and over by people whose job is to spend limited money where it returns the most knowledge. But here's where it gets strange. Venus may not always have looked like this. Newer climate models, together with a ratio measured in its thin upper air, the balance between ordinary hydrogen and its heavier cousin deuterium, suggest Venus once carried real water, maybe shallow oceans spread across the whole globe, tens to hundreds of meters deep, in effect. Venus also sits closer to the sun than Earth does, and closer means hotter. As it warmed, water evaporated into the air. Water vapor traps heat, so the evaporation fed more evaporation, and more evaporation trapped still more heat. At some point, the process may have crossed a line it could not walk back from. The oceans boiled away completely. The freed hydrogen escaped into space, light enough to drift off the top of the atmosphere. The carbon dioxide left behind had nowhere to go and nothing left to absorb it. So it simply stayed, thickening year after year. Not a slow decline. A locked-in, permanent runaway furnace. So the planet we quietly wrote off is not simply a random hell world sitting next door. It may be the one nearby example of what happens when an Earth-sized world tips past the point where it can still hold onto a livable climate. The same kind of tipping point scientists still worry about closer to home. Exactly how much water Venus once carried, and how quickly the balance tipped, is still being pinned down, but the direction of the evidence keeps pointing the same way. Asking why we never went back to Venus turns out to be asking something larger. Why we have not pushed harder to study the one nearby world that shows us how badly this can go. And understanding exactly how Venus lost that fight starts with something closer to the ground than oceans or greenhouse gases. It starts with what happens to a machine in the first few seconds after it touches down. The air alone is the first thing that reaches it. Not dust, not rock, not a jolt on landing. Just air, sitting at about 462 degrees Celsius, pressing into every seam of the machine before the machine has done a single thing. Room temperature back on Earth sits around 20 to 25 degrees. High-performance chips, the kind running inside a laptop or a car's engine control unit, tolerate maybe 80 to 100 degrees if something is actively cooling them. Venus does not offer a spectrum to negotiate. It offers a wall, and the wall sits at roughly 3 times the temperature most electronics ever expect to see. Call it an everything in your toolbox has already failed number. Cross that wall, and the parts fail in a specific order. Epoxy glue holding components in place breaks down chemically. Solder joints creep and pull apart. The plastics in wire insulation, in circuit board material, in cable jackets, carbonize and crack and outgas into a sealed box with nowhere to vent. Lubricants in bearings cook down to a dry crust. Some steels start to lose their strength. Lead, if any happened to be on board, would simply run. None of these failures happen in isolation either. A cracked cable jacket exposes bare wire to a socket that is also creeping loose, and a bearing running dry seizes a motor that was already fighting warped housing. The machine does not fail once. It fails in a slow, compounding cascade, each broken part making the next one fail faster. Better materials do not fully fix this. Ceramics, exotic alloys, high-temperature polymers all help at the margins. But the entire discipline of spacecraft electronics rests on one quiet assumption, that the inside of the box stays under roughly 120 degrees no matter what the outside is doing. Venus breaks that assumption before the lander even reaches the ground. There is no night on the surface to cool things down, no season change, no polar ice sheet holding the average low, just heat above 460 degrees, constant, pressing in from every direction, forever. That is the first hammer. The second is pressure, about 92 times what a person standing at sea level on Earth feels. Engineers who build for pressure like that usually build submarines, and submarines sit in cold, calm, forgiving seawater. Venus offers no such mercy. The same square centimeter being crushed is also being cooked, so the hull carries two jobs at once. It has to behave like a deep sea pressure vessel, something between a submarine hull and a bomb casing, and it has to do that while shrugging off furnace heat that never lets up. Most structural metals get weaker as they heat, right when the pressure load stays exactly as punishing as ever. So the margin engineers count on at room temperature quietly shrinks the moment the lander touches down. The usual answer is thick titanium, wrapped in ceramics and insulation. Thick metal is heavy. Heavy means a bigger rocket, a bigger budget, and none of it touches the temperature problem still waiting on the other side of the wall. Wait. Here is where the physics turns actively hostile rather than merely difficult. On Mars, engineers fight to hold on to heat, because the air is thin and the nights are brutally cold. On Venus, that fight flips completely. You are trying to get rid of heat, and the planet will not let you. Heat moves in through 3 separate paths. Conduction pulls it up through the lander's feet from ground that stays hotter than the machine sitting on it. Convection pushes it in sideways because the atmosphere is so dense it behaves less like air and more like a slow, heavy fluid. Radiation, the one path that should offer an exit, barely works at all, because radiative loss only functions when you are hotter than your surroundings, and the surroundings are already above 460 degrees. Shade will not save you. Blocking sunlight sounds like it should help, and on Mars or the Moon it does, but on Venus, the atmosphere itself is the heat source, hotter than most industrial ovens, and shade does nothing to an oven wall. Active cooling will not save you either. A radiator only works by dumping heat into something cooler, and Venus's cool side is already 462 degrees. Coolants that work fine on Earth boil, decompose, or simply react with the surrounding gas before they can carry anything away. Push harder with the refrigeration, and you need more electrical power. More power means a bigger power source, and a bigger power source makes more heat that also has to go somewhere. You end up chasing your own tail, all packed into something roughly the size of a car. So the engineers who built the first landers stopped fighting the heat and started outrunning it instead. Treat the whole lander as a giant insulated thermos. Chill the electronics hard before launch. Wrap them in thick walls and insulation. Accept, from the first design meeting, that the inside temperature will climb no matter what, and simply race to finish the mission before it climbs too far. That race has a fixed, brutal shape. Data from the landers show internal temperatures rising steadily the moment they touch down, even behind titanium pressure vessels and layers of ceramic insulation. Sensors failed first, communications degraded next. Then, the core electronics shut down, one after another, leaving an intact metal shell wrapped around a dead brain. Not a malfunction, not bad luck. A countdown to thermal death, decided by the laws of heat flow before the spacecraft ever left the launch pad. running somewhere between 60 and 90 minutes. Put that number in front of a funding committee, and the conversation writes itself. Would you rather pay for a lander guaranteed to die on schedule within the hour, no matter how well it is built, or a Mars rover that keeps driving for a decade? On Venus, every design choice traces back to that single, unforgiving fact. The surface was never going to give anyone more time. The only question left was what could be learned before the clock ran out, and that question would decide what came next. The heat and the pressure at the surface do not begin at the surface. They arrive from above, carried down through a sky that is not simply sitting there, waiting. Call it an invisible ocean of hot gas, one that crushes and cooks at the same time, hundreds of kilometers deep, moving in ways no submarine captain on Earth would recognize. Start with what it is made of. Roughly 96 to 97% carbon dioxide, the rest mostly nitrogen, with a scattering of trace gases folding in and out of the clouds. Near the ground, the density of that mix runs past 60 kilograms per cubic meter. Earth's air, for comparison, sits around 1.2 kilograms per cubic meter. Do the division and Venus comes out roughly 50 times denser, close to what a diver feels a short way underwater, except this water is not water. It chokes, it presses, it cooks. Set the temperature aside for a moment and just feel the thickness of it. Moving through gas this dense would feel less like breathing air and more like pushing through a light fluid, a texture with weight and resistance to it, the way water resists a hand dragged through a pool. Density is not a single favor either. It helps in one narrow way, slowing a falling spacecraft faster than thin Martian air ever could, cushioning the descent before a parachute even opens. But that same thickness turns descent into a fight against massive aerodynamic force, extreme heating, and mechanical stress on anything moving through it at speed. The atmosphere is not just a medium to fall through. It shapes how heat travels, how energy moves, and how quickly a surface gets attacked. Then comes a second shock, and this one has nothing to do with density. Venus itself turns slowly, one full rotation every 243 Earth days, slower than its own year around the sun. But the atmosphere above the clouds refuses to wait for the ground beneath it. At cloud top altitude, around 60 to 70 kilometers up, the entire gas envelope circles the planet in roughly 4 days. Winds up there reach close to 100 meters per second, nearly 360 kilometers an hour, about 220 miles an hour. A hurricane that never makes landfall, one that never loses strength, one that wraps clear around the globe and never stops. A permanent Category 5 gale with nowhere left to blow itself out. Near the ground, the wind slows, held back by drag and rough terrain, part of why the Venera landers were not simply flipped over on arrival. But before anything reaches that calmer air, it has to fall through the fast layer first. Parachute fabric and rigging get struck sideways while already superheated. A floating platform, a balloon or an airship would live permanently inside that jet stream, taking constant lateral force, twisting load, and slow fatigue on every cable, seam, and strut it owns. But here's where it gets strange. The clouds themselves, sitting between about 48 and 70 kilometers up, are not made of water at all. They are sulfuric acid, droplet after droplet of it, suspended the way water droplets hang inside a cloud on Earth. On Earth, acid rain is something clean air turns acidic on the way down. Not a byproduct here. The cloud itself is the acid. Any exposed metal, coating, or seal that cannot resist it corrodes, pits, or weakens over time, and even fine vapor drifting off the droplets attacks bare surfaces. Optics take the worst of it. Ordinary glass will not stay clear. Engineers reach for sapphire windows and protective coatings instead, and even those slowly lose their sharpness. Anything meant to survive out there for long has to assume it is under continuous chemical attack from the moment it arrives. Some of what this atmosphere does, no one has fully mapped yet. There is evidence of lightning, likely tied to convection and charge building inside the clouds. There are dark streaks visible in ultraviolet light, patches that absorb more radiation than the clouds surrounding them. Complex sulfur chemistry is the leading explanation. A handful of researchers have floated stranger ideas involving airborne microbial life, far from proven. closer to a curiosity than a hypothesis with support behind it. What matters to a mission designer is simpler than the explanation. This is a chemically active, electrically active atmosphere, and telling a review board overseeing a mission worth hundreds of millions of dollars that nobody is quite sure what a layer of the sky will do next is not a sentence that gets funded. There is one band that looks almost forgiving. Between about 50 and 60 kilometers up, pressure settles near 1 bar, close to sea level back on Earth, and temperature sits in a range of roughly 20 to 70 degrees Celsius, close enough to a warm room that a balloon riding there would not need a furnace-proof hull. For a moment, it sounds like an opening. It is not. That same band still carries the acid droplets, the 100 meter per second winds, and the ultraviolet flux. So a platform built to live there needs the same acid-resistant skin, the same fatigue-hardened structure, the same shielding as anything closer to the ground. Friendly numbers, unforgiving neighborhood. Even a spacecraft that never intends to touch any of this does not get to skip it entirely. Orbiters sit above the worst of the weather, but the outer edge of Venus's atmosphere still reaches up to meet them. Thin gas and charged particles from the sun dragging quietly at anything that flies low enough to map the surface in detail. That drag nudges orbits off course over time, small at first, then compounding, and correcting it costs fuel, carried up from Earth in the first place, fuel that cannot be replaced once it is gone. Dip lower on purpose, the way engineers do during aerobraking to save that same fuel, and a wrong guess about density at that altitude can mean overheating or structural loads nobody planned for. A mission that never touches the ground can still be quietly worn down by a sky it was only ever supposed to fly over. So the sky is not a boundary a spacecraft crosses once on the way down. It is an adversary present at every altitude, dense enough to crush, fast enough to tear, acidic enough to eat through anything left exposed. And even the ships that never planned to land inside it are not entirely safe from it. What waits at the bottom of that ocean of gas would turn out to be the easier half of the journey. That same sky, the one already quietly wearing down orbiters far above the clouds, is also the wall every mission has to punch through just to arrive. For a human crew, it would have to be punched through twice, once coming down, once going back up. On a map, Venus looks like the shortcut. It orbits the sun at roughly 72% of Earth's distance, tucked in close, while Mars sits out at about 1.5 times Earth's distance, well beyond us. A transfer to Venus can burn less fuel than a transfer to Mars, and it runs faster too. Roughly 4 to 5 months of quiet cruising against 6 to 9 months for Mars. Closer, quicker, cheaper. That is the first impression, and it is the one a simple chart shows. A chart only tracks the cruise though. It says nothing about arrival. Getting to Venus is not the same problem as getting into it, or down onto it, without tearing the spacecraft apart in the process. Slowing down usually means diving straight into the atmosphere instead of burning huge amounts of fuel. And diving into Venus means hitting thick carbon dioxide at somewhere around 11 to 12 kilometers a second. Put a number like that on the ground, and it is fast enough to cross the continental United States in about 4 minutes. Energy does not rise in a straight line with speed either. It rises with the square of it. So a little more velocity means a lot more heat. Venus combines that higher entry speed with a far thicker atmosphere than Mars offers, and the two together produce extreme heating and enormous mechanical load at the same time. A heat shield built for Mars would be underbuilt for Venus. The front face has to survive peak temperatures and peak pressure at the same moment, while the structure behind it carries the load without buckling under the shear. Getting one that actually holds means heavier, more complex, more expensive engineering. All of it spent before a single second of surface science begins. On Mars, the trouble is air too thin to slow anything down, so landings lean on heat shields, parachutes, retro rockets, whole sky crane systems fighting thin air every step of the way. On Venus, the trouble runs the other direction entirely. The air is so dense a spacecraft hits it like a wall, deceleration spiking to several times the pull of Earth's gravity, hard enough that the structure, the parachute lines, everything bolted inside has to be built to take that hit and keep working. Parachutes have to open already, supersonic, inside superheated, high-pressure carbon dioxide with dynamic pressure on the canopy that would shred an ordinary chute before it even fully opened. The Soviet answer looked closer to artillery design than aviation. Blunt aeroshells first, parachutes next. Then, in the thickest lower air, simple drag devices instead of fabric, because a parachute would not have survived down there anyway. Each phase was tuned for one purpose, staying in one piece long enough to reach the ground, not landing gently, but arriving intact. The answer was stranger than expected. Landing, brutal as it is, still is not the hardest problem. Wait, getting a spacecraft down to Venus is not what ends a human mission. Getting one back up is. An ascent vehicle would first have to sit on the surface, inside pressure 92 times higher than Earth's, and heat well past 460 degrees Celsius, hot enough that many metals begin to lose their strength, and only then ignite its engines and climb straight up through that same crushing, superheated air. Earth's own atmosphere at sea level is already a serious problem for a rocket trying to leave the ground, drag and pressure fighting the engines from the first second of ignition. Venus multiplies that pressure by roughly 92 and adds heat that ordinary engineering metals cannot hold their strength against. Surviving down there long enough to launch, let alone launching successfully, would take extreme structural strength, heavy insulation, propellants that stay stable at high temperature, and enough fuel to fight through thick, hot air all the way to orbit. Every one of those requirements adds mass. More mass means a bigger lander to carry it, a bigger heat shield to protect the bigger lander, a bigger rocket back on Earth to launch the bigger heat shield. The stack grows until it stops being realistic as a first step for a human being, not a harder landing. An engineering wall no serious mission plan has found a way through yet. It is the reason plans for stepping beyond the moon point toward Mars rather than Venus. Launching from the surface, there would mean lighting a rocket inside a furnace at the bottom of an ocean. Heat and crushing weight pressing on the engines from every side at once. None of that touches a spacecraft that stays above the clouds. An orbiter still delivers gravity assists, radar mapping of the surface, years of study on winds, temperature, and the solar wind's pull on the upper air, controlled aerobraking to trim its own orbit, all without ever meeting the ground below. A full mission to the surface pays for a heavy shield, a reinforced structure, and a descent system built like the ones just described, in exchange for, at best, a couple of hours of data once it finally arrives. Review boards watch the cost and the risk climb, while the expected lifetime keeps shrinking, and lean toward the platform that keeps working for years instead of minutes. Meanwhile, a Mars mission promises both a rover that keeps driving for years and a stepping stone toward eventual human travel. Two reasons to fund it against one short, brutal window on Venus. That same arithmetic only gets sharper once the full economics of launch windows and mission budgets get laid out in full. Every part of it assumes the machine never has to touch the ground. The ones that do still have another fight waiting for them, one that has nothing to do with heat, pressure, or a violent fall at all. Set aside how hard it is to arrive. A lander that survives the fall through Venus's atmosphere is still not safe once it settles onto the ground, because the air around it never stops working on it. Being inside that air is like sitting inside a chemical reactor that never turns off, one running hundreds of degrees above anything the hardware on board was ever built to tolerate. The atmosphere is close to 97% carbon dioxide, with most of the remainder nitrogen, plus smaller measures of sulfur dioxide, a corrosive gas, trace water vapor, and other sulfur compounds. At the surface, in heat well past the point that melts lead, ordinary chemistry speeds up. Reactions that would take years at room temperature finish in hours. Some finish in minutes. Metals oxidize fast in that heat. Normally a thin oxide layer forms on a metal surface and then stops the reaction. A kind of self-sealing skin, the metal grows over itself. So, what happens to a metal that can never quite finish growing that skin? On Venus, the layer cracks before it seals. It flakes. It never stabilizes. The metal underneath keeps reacting, layer after layer, instead of protecting itself the way it would in a cooler world. Add sulfur dioxide, trace water vapor, and that same heat together, and the mixture manufactures sulfuric acid directly against the hull. Structure, fasteners, connectors, every exposed joint ages on a clock, measured in hours, sometimes minutes. Standard aerospace bolts and rivets, chosen everywhere else for strength and low weight, corrode first at the threads, the one place a visual check on the launch pad can never catch. 3 things are stacking on top of each other here. First, the heat alone speeds up every reaction. Second, the atmosphere supplies exactly the ingredients, sulfur and trace water, that turn ordinary oxidation into acid attack. Third, the one defense a metal would normally lean on, that thin protective skin, is the first thing this air destroys. None of the 3 waits for the others to finish. That is the surface. Higher up, between roughly 48 and 70 kilometers, thick clouds of sulfuric acid droplets ride winds near 100 meters a second, the same fast band already circling the planet. Each droplet that strikes a spacecraft on the way down is its own small corrosion event, a spray of acid at hurricane speed, not the slow acid rain Earth sometimes sees. Aluminum alloys and ordinary stainless steel, the metals that make up most spacecraft, do not hold up in hot acid. Coatings peel, pits form, strength drops. None of that damage waits for touchdown. It starts the moment a descending capsule punches through the acid layer, hours before the ground is even in view. So the list of usable materials narrows fast. Titanium alloys resist the acid better than steel. Advanced ceramics barely react at all. Fluoropolymer coatings, the same chemical family behind non-stick cookware, add one more layer of resistance. Each option costs more, takes longer to manufacture, and is harder to certify for flight than the metals a Mars mission gets to use straight off the shelf. What starts as an ordinary spacecraft parts list ends as a specialized Venus-only machine, built from a shopping list almost no other mission needs. Moving parts face the same siege. Hinges, bearings, antenna deployments, sample arms, instrument covers, all depend on lubricants and seals to move without seizing. Ordinary oils and greases survive to a couple hundred degrees at most, then break down or burn away. Venus sits far past that line already, and its air adds reactive gas and acid on top of the heat. Dry lubricants, powdered graphite or molybdenum disulfide, a soft mineral that coats metal instead of an oil, hold up better at extreme heat, but even those can change chemically in sulfur-rich air. Rubber and polymer seals harden, crack, or dissolve outright, so every joint on the machine needs a decision made months before launch. Seal it away in a cooler compartment, or build it to move without any conventional lubrication at all. Get that decision wrong on one hinge, one drill, one antenna, and that part of the mission ends, even while the rest of the lander is still technically alive. A sample arm that cannot fold back stays extended for whatever time is left. A dust cover that will not swing open never uncovers the lens underneath it. There is no repair crew to send, not a crushed hole, a frozen joint. Cameras, spectrometers, laser rangefinders, and radiometers all depend on a clean path for light, clear windows, lenses, mirrors that stay untouched. Acid vapor and reactive gas etch ordinary glass, eat through coatings, and roughen surfaces until images blur and readings drift. A laser aimed at measuring distance or composition needs that same clear path. And a beam scattered by a pitted window is a beam that no longer tells the truth about what it hit. Sapphire windows and specially hardened glass slow the damage. They do not stop it. That produces an uncomfortable timeline. A lander might survive 90 minutes on the surface, but if the camera window pits or fogs in the first 20, everything the lens sends back after that is close to useless. A clogged gas inlet does the same thing to a spectrometer. The readings drift, then stop, long before the electronics themselves fail. The body outlasts the eyes. None of this is unsolvable. Long ovens running simulated Venus air, material screening, tougher coatings, thicker acid-resistant shells. Enough testing and enough money can build a machine that beats every Soviet lander that came before it. But weigh that bill against Mars, or against the icy moons further out. Mars lets engineers use standard, space-rated metals and lubricants off the shelf. worrying about dust and cold rather than hot acid. Icy moons bring radiation and cold, but nothing that eats a hole from the outside in. Venus narrows the parts list, complicates every test, since heat, pressure, and reactive chemistry all have to be checked together rather than one at a time, and stacks uncertainty on uncertainty. For the cost and risk of one short-lived Venus lander, 2 or 3 Mars missions can fly instead. So the chemistry, expensive as it already is, turns out not to be the whole argument against going back. Solve every one of those corrosion problems, and the lander still has to think. Venus has never once let it. Say you win every fight already fought. The heat outside, the pressure squeezing the hull, the acid eating at every seam. None of that spares what sits inside the machine. A spacecraft still has to think. And thinking on Venus means running a computer inside a room that is already hot enough to have killed the chip before it ever switched on. Modern spacecraft electronics, the processors, memory, power controllers, sensor interfaces, are built from silicon designed to operate around 20 to 25 degrees Celsius. Push a space-rated part hard, and it can survive somewhere near 120 to 150 degrees, roughly the setting of a moderate kitchen oven. That ceiling is not a rough guess. It comes from decades of testing every part that flies, and it holds for the processors driving a Mars rover just as much as for the sensor package on a lunar lander. Past that line, the transistors start leaking current even when they are supposed to be off. Junctions lose their sharp switching behavior. Threshold voltages drift. Timing margins shrink until a logic gate fires too early or too late, and a single mistimed switch turns into a flipped bit, a corrupted number, a wrong instruction. None of this arrives as a dramatic failure. It arrives as a chip that quietly stops telling the truth. Venus surface air sits at about 462 degrees. That is roughly 3 times hotter than the oven setting that already pushes silicon toward its limit. Not a harsher version of the same problem. A different physical regime. One ordinary electronics were never built to enter. The Soviet answer was not to fight that heat directly. It was to hide from it for as long as possible. Venera landers carried their electronics inside heavily insulated, pressure-hardened shells. Something between a deep-sea pressure sphere and a thermal bottle pushed past its design limits. Before arrival, the inner chamber was chilled well below the outside temperature, sometimes with phase-change materials or heat-absorbing tanks doing the cooling. So the electronics crossed into the atmosphere already carrying a head start against the heat waiting outside. After touchdown, the outside held steady past 460 degrees, while the inside started cold and climbed. Every additional minute of survival on Venus, in other words, had already been paid for on the launch pad, chilled and sealed in before the rocket ever left the ground. Heat crept through the walls and the insulation, patient and constant, an electronics bay working as a thermal time bomb. Venera 7 ran for about 23 minutes. Venera 13, the record holder, lasted close to 2 hours. Neither one failed. Both did exactly what the physics guaranteed they would do, on a schedule set the moment they were sealed shut on Earth. Longer missions need something that does not have to hide. Wide bandgap materials, silicon carbide and gallium nitride, behave differently at extreme heat than ordinary silicon does. In laboratories, simple circuits built from these materials have run at 300 to 500 degrees for hundreds of hours, sometimes thousands of weeks of continuous operation stacked end to end. Not the countdown a landed spacecraft gets today. In principle, a lander built around this technology could sit exposed on the surface and keep working long after an old Venera shell would have gone dark. But here is the catch nobody gets to skip. What labs can reliably build are still mostly simple devices, basic logic gates, straightforward amplifiers, a handful of sensors. A working spacecraft needs a fast processor, deep memory, complex communications, radiation hardening, and fault tolerance, all proven together as one system. Nobody has built and space qualified that whole stack at Venus temperature yet. A lander flying entirely on this hardware today would be flying frontier equipment, not the conservative. Decades proven electronics an agency risks $1 billion on. But the biggest gap was never just the chip, it was the power behind it. Most spacecraft run on solar panels and batteries. On the Venus surface, solar is nearly worthless. The thick clouds block most direct light before it ever reaches the ground. Ordinary lithium-ion batteries, the kind inside a phone or a satellite, are unsafe well below Venus temperatures, prone to venting or catching fire long before the air outside reaches its worst. Even specialized high-temperature chemistries give out far short of 460 degrees. What is left are molten salt batteries, which only work as a battery once they're already hot, and radioisotope thermoelectric generators, RTGs, drawing power from the heat of radioactive decay already flying on Voyager and on Curiosity. Both are promising. Neither is a simple swap. An RTG built for the cold, thin vacuum around Mars carries its own shielding and cooling, tuned for a completely different environment, and none of that tuning survives a redesign into a pressure vessel that must also fend off acid and crushing weight. You cannot bolt a Mars rover's power source onto a Venus lander and call the problem solved. So why has nobody just built this? First, solving Venus electronics in full would take a large, focused investment against space budgets that are never large enough. Second, agencies favor technology that pays off more than once, and high-temperature electronics serve Venus, a handful of industrial uses on Earth, and maybe a deep atmosphere probe at a gas giant, a short list. Third, radiation-hardened electronics built for milder temperatures already serve Mars rovers, lunar landers, asteroid probes, and outer planet orbiters, nearly everything else currently flying. Money follows the technology that works everywhere, not the technology that only works on one furnace of a planet. That is the loop. Few Venus surface missions fly, so there is little case to invest in the hardware Venus needs. Without investment, the technology stays immature. Immature technology makes any proposed mission look risky. Risky missions do not get approved. And with no missions flying, the case to invest never grows. The cycle closes on itself and starts again exactly where it began. The planet that may matter most for understanding what extreme climates can do to a world is also the one demanding an entirely new generation of hardware just to buy a few more hours of data. Nothing about that hardware is impossible. It is only unbuilt, waiting on a loop that has not yet found a reason to break. Add up every one of those countdowns, every minute any lander spent transmitting from the ground, and the total is smaller than most people would guess. Venera 7 gave about 23 minutes, the first time any spacecraft had soft landed on another planet at all. Venera 9 gave about 53 minutes. Venera 13, still the record holder, gave close to 2 hours before its electronics cooked. The Vega landers, which also released balloons higher up on the way down, each managed roughly an hour on the surface before falling silent in turn. Stack every working second from every successful landing in history, every reading, every frame, every crackle of telemetry, and the sum comes out to only a few hours. Not a few hours per mission. A few hours total for an entire planet, across more than a decade of trying. Not a rounding error. The entire surface record of Venus, every soft landing humanity has ever managed there, adds up to less than a single work week's commute. A whole planet reduced to a stretch of time most people spend getting to an office and back. So what did those brief windows actually buy? Temperatures around 450 to 470 degrees Celsius, matching what later missions would confirm again and again. Pressure near 90 to 95 times what Earth's air pushes down at sea level. An atmosphere dominated by the carbon dioxide, with nitrogen as the main secondary gas and clear traces of sulfur dioxide riding along with it. Rock spectra that matched basalt, the same dark volcanic stone found on Earth's ocean floors and old lava plains. Humidity readings that came back essentially at zero. No trace of water vapor sitting in that furnace air. And the only true surface photographs humanity has ever taken of another world's ground up close. Flat fields of broken rock and gently rolling stone under a hazy, yellowish sky, the horizon low and indistinct in every direction. No lush valley waiting just past the frame, no hidden oasis the cameras happened to miss. Every image showed more of the same. Here is where the read on that data turned decisive. A thick carbon dioxide atmosphere loaded with sulfur, sitting over a surface that was extremely hot, extremely pressurized, made of dry volcanic rock, with no pond, no lake, no shaded lowland offering a break from any of it. Planners in the 1970s and 80s were not looking at an ambiguous puzzle. They were looking at a planet-wide worst case for life and for hardware, all confirmed within the same couple of hours. No liquid water, no mild pocket, no cooler basin tucked somewhere out of the heat, just uniform, global hostility, repeated at every landing site that ever reported home. Mars, in the same years, was doing the opposite. Dried channels that once carried something, minerals that only form in the presence of water, polar caps holding visible ice. Later, strong evidence for more ice hiding just beneath the ground. Cold and thin-aired? Yes, but a place that had clearly once been wet, and might still be chemically interesting today. Two neighboring worlds, studied by the same generation of engineers, moving in opposite directions in the public imagination. One narrowing toward a hard no, the other opening toward more questions than it answered. And the lifetimes told their own story. A Venus lander brought minutes to hours of data without years of new technology behind it. A Mars rover with existing hardware already ran for years, sometimes more than a decade past its planned mission, measured against the money spent, against the time invested, against the sheer number of readings each dollar bought. Mars was returning far more science for far less risk. That comparison did not need to be argued hard in front of a review board. The numbers made the argument on their own. Something quieter shifted underneath the science too. Before those landings, Venus had been a mystery world, thick clouds hiding an unknown surface that could, in principle, have held almost anything. After them, it became the planet everyone already understood. Awful and proven awful, a settled fact rather than an open question. And once a destination stops being a mystery, the center of gravity in a space program moves elsewhere, away from landing, toward orbit. Orbit turned out to be generous. NASA's Magellan, launched in 1989, used radar to see straight through the clouds, mapping about 9% of the surface in the early 1990s down to a resolution of hundreds of meters. Volcanoes, impact craters, wide plateaus, long rift zones, and entire hidden geology revealed without a single pressure vessel touching the ground. Later, in the 2000s and 2010s, Europe's Venus Express and Japan's Akatsuki studied the atmosphere itself from above, tracking wind patterns, the superrotation, temperature layers, and how the upper air interacts with the solar wind. Years of steady data, gathered patiently, one orbit at a time. No 90-bar haul to design, no hour-long clock ticking down to silence, no thermal time bomb sealed inside an insulated shell. Just distance, and the safety distance bought. But here is the part that outlasted the missions themselves. Venus became, in the institutional memory of the people who fund these programs, the place already proven awful. A cautionary slide in a review meeting, not a live proposal. The big questions of that era, whether there was life, whether the surface was survivable, whether working there was realistic, all came back with the same answer. No. Mars kept a door open. Past life, buried life, ice a future crew might use, an unfinished story that still pulls in funding. Venus's story looked finished, not a case of the landers failing. The opposite. They worked exactly as designed, and worked so completely that they closed their own future. Every image, every temperature reading, every crushed pressure gauge added up to an answer so total that almost nobody has felt the need to ask the same question twice. If a mission already looks like a settled no, and the hardware to ask again still dies within the hour, the case to spend billions confirming it one more time gets harder to make every year that passes. That verdict held for decades. It was not, it would turn out, quite as settled as it looked. That reputation is not just a feeling. It shows up, very concretely, every time a launch window opens and someone has to choose what to fund. Venus and Earth line up for a good transfer window roughly every 19 months, about the same rhythm Mars keeps. Every year and a half, a small group of people with a fixed amount of money and a fixed number of rockets has to decide what actually flies next. When there is only room for one more mission, why does Venus so rarely get picked? It is never the only name on the list. Mars wants another rover. Europa and Ganymede want to look under their ice. Titan and Enceladus want their own dedicated probes. Near-Earth asteroids want attention for planetary defense. Outer solar system flagships want to turn after decades of waiting quietly in line. There is no separate Venus fund sitting untouched somewhere, waiting to be spent. There is one pot of money, one set of rockets, and a stack of proposals that all sound reasonable on paper. Inside that competition, an orbiter has an easy case to make. It can run for years. It maps the surface with radar, tracks the winds, gauges temperature layers, and watches the atmosphere shift season by season, all at moderate risk, using technology that has already flown and already worked. Landing bends that curve the wrong way. Costs climb, a heavier heat shield, a reinforced descent stage, a pressure vessel built for 92 bar, materials chosen to fight acid instead of dust. And while the cost climbs, the lifetime falls, from years down to minutes, maybe an hour if everything goes right. Not a lack of curiosity. A ledger problem, one that gets a little worse every time somebody runs the numbers again. Put a Mars rover next to a Venus lander, and the mismatch sharpens fast. Opportunity was designed for about 90 Martian days, and kept driving for almost 14 Earth years. More than a decade of bonus science nobody had budgeted for. Curiosity is still working. Perseverance is still working too. Drilling? Caching samples for a return mission that has not launched yet. Now picture standing in front of a funding committee with a Venus lander priced about the same as one of those rovers, and telling the room it might survive an hour. Watch the room lean away. Not because the science lacks value, because the return looks small next to a rover built to run for a decade, an orbiter circling Europa's ice, or a mission that might someday nudge a hazardous asteroid off its course. Here is the quieter half of the story, the part that rarely makes it into an official proposal. Human exploration pulls public attention in a way robotic missions never quite manage, and the Moon and Mars both fit a story people already want to hear. Habitats built into lunar regolith, local ice turned into water and breathable air, rovers, greenhouses, a plausible sentence that starts with "someday we live there." On Venus's surface, that sentence collapses before it finishes. At 90 plus bar and somewhere close to 460 degrees Celsius, unprotected human survival on the ground sits at essentially zero, and no reasonable near-term engineering changes that math. What you can build down there is a short-lived science capsule, not an outpost. Even the more hopeful idea, cities drifting in the clouds, sits decades out, carrying its own separate pile of unsolved problems. Not a foothold for a spreading species. A sealed instrument, on the clock from the moment its engines light. So Venus cannot ride the wave that carries Mars. The promise of somewhere a person might eventually stand. And that matters more than agencies like to admit. Because a mission that only returns data gets judged by a different, quieter standard than one that also returns a future address. There is a third quiet strike against it, and it has nothing to do with romance or public imagination at all. Agencies favor technology that pays for more than one trip. A heat shield, a parachute system, a descent stage built for Mars gets reused, refined, and flown again on the next Mars mission, or borrowed for a human lander further down the road. Learning to live off Martian or lunar soil feeds directly into every future base concept still on the drawing board. Lunar work feeds programs planning a permanent moon presence. Even asteroid missions double as planetary defense and future mining studies. Venus offers almost none of that. Its extreme environment calls for electronics that tolerate temperatures nothing else in the solar system demands, materials chosen for one planet's specific chemistry, systems that solve Venus, and mostly only Venus. A committee weighing two proposals of similar cost will almost always favor the one that helps 5 future missions over the one that helps just one. Not a small preference. The deciding factor, quietly, again and again. Add it up, and Venus gets sorted into 2 separate columns. Orbiters, atmospheric probes, flybys, strong science, manageable risk, reasonable cost, approved. Landers, custom hardware, high risk, a lifetime measured in minutes, deferred one more time to the next window. None of this is a grudge against one planet. It is a spreadsheet, Run honestly, arriving at the same conclusion for more than 40 years running. But the spreadsheet was only ever measuring one side of the question. While the economics kept pushing landers off the schedule, the science case for going back was quietly getting stronger, not weaker. The planet everyone had already filed away as a settled no was about to look like something else entirely. The clearest warning sign in the solar system, sitting exactly where the money had stopped looking. The budget only ever asked what a mission would cost and how long it could survive. It never asked what the atmosphere itself was already saying to anyone willing to read it. We do not have a single rock from the Venusian surface sitting in a lab on Earth, but the air above that surface carries something almost as good, a fingerprint left behind by whatever the planet used to be. That fingerprint is a ratio, deuterium to ordinary hydrogen, DH for short. Deuterium is heavy hydrogen, an atom carrying an extra neutron. Ordinary hydrogen is lighter, and lighter atoms drift off into space more easily over billions of years. So when a planet loses most of its hydrogen, the heavy kind gets left behind in greater and greater proportion, and the ratio climbs. Venus's ratio is not a small bump above Earth's. It is far higher, high enough that the simplest explanation left standing is that Venus once carried enormous amounts of hydrogen, and almost all of it is gone now. Run the models backward from that single number, and they converge on the same picture. Tens to hundreds of meters of water spread across the entire globe. Picture that depth stacked up, from the height of a modest apartment building to the height of a downtown high-rise, poured over every square kilometer of the planet. Not puddles, real oceans, real lakes, real seas, by any ordinary use of those words. Which means the numbers from the very start of this story were never just decoration. The near-Earth gravity, the near-Earth size, the same star, the same rough distance from it, all of it was quietly pointing at a planet that may once have looked wet, blue in patches, close enough to familiar. Not an alien world bolted onto our solar system by accident. A near cousin of early Earth, sitting one notch closer to the sun. Here is where the story turns dark. At its distance from the sun, Venus receives close to twice the sunlight landing on every square meter of Earth. An ocean-covered planet sitting in that much extra sunlight warms faster than Earth ever has. Warmer oceans evaporate faster. Water vapor is itself a powerful greenhouse gas, so more vapor in the sky traps more heat, and more heat evaporates still more water. Warming feeds evaporation. Evaporation feeds warming. Round and round, each pass loading more fuel onto the next. A feedback loop like that is not automatically fatal. Earth runs loops of its own and stays in balance. But past a critical point, the water vapor thickens enough that the planet can no longer shed heat back to space fast enough to cool down. The climate stops correcting itself. It only accelerates. The oceans did not fade away slowly. They boiled, not across one bad summer, across a long stretch of geological time, but with no breaks anywhere in the system and no route back to where it started. High in the atmosphere, ultraviolet light tore the rising water vapor apart, splitting it into hydrogen and oxygen. The hydrogen, light and quick, drifted off into space, the same drift the DH ratio is still recording today. The oxygen mostly reacted with surface rock or left with it. Meanwhile, carbon dioxide, pouring endlessly out of Venusian volcanoes, had nowhere left to go. On Earth, that carbon dioxide would eventually get pulled back down, weathered into rock, folded into ocean sediment, cycled by what is called the carbon silicate cycle, a slow thermostat that has kept Earth's climate on a leash for billions of years. Venus lost the ocean that cycle depends on. Without liquid water sitting on the surface, there was nothing left to lock the carbon dioxide away. It simply piled up and stayed. Not a slow drift into a warmer climate. A one-way door, and it locked from the outside. What is left today is the atmosphere every lander and orbiter since has measured, thick with carbon dioxide, almost no water at all, a surface locked at roughly 462 degrees. Not a harsh climate, a finished one. Climate scientists are not claiming Earth is about to follow the same road. The timescales are different. The starting conditions are different. Nothing currently underway on Earth matches what Venus went through. But that does not make Venus irrelevant to Earth. It makes it essential. Venus is the only nearby example of a rocky, Earth-sized planet that crossed the point of no return and kept going. Earth shows what balance looks like from the inside. Venus shows what happens once that balance is gone for good. For years, the working habit was to treat Earth alone as enough data to understand rocky planet climates. That habit has it backward. One working example teaches you what stability feels like. It does not teach you where the edge sits. Venus is the only other data point close enough in size and history to show where that edge actually is. The same question now reaches far past our own solar system. Telescopes like Kepler and TESS have found thousands of planets circling other stars, plenty of them close to Earth's size, plenty of them sitting inside or near their star's habitable zone. But size and orbital distance alone cannot tell you what kind of planet you are looking at. An Earth-sized world at the inner edge of a habitable zone could be a genuine ocean world, or it could already be a Venus, thick with carbon dioxide and sulfuric acid cloud, having already crossed that same one-way door. From a telescope light years away, those two planets can look almost identical. The only way to tell them apart is atmosphere and history, exactly the record Venus is still holding onto. Study its atmosphere closely enough, its thickness, its chemistry, how heat moves through it, and you build a template for sorting real Earths from Venus analogues among the stars. Skip that step, and a fair share of the planets currently filed under promising may turn out to be worlds that already crossed over. That is when the pattern broke. The more essential Venus becomes to answering that question, the less equipped we are to look. Our last successful surface mission touched down in the early 1980s, more than 40 years ago. The high-temperature electronics, the acid-resistant materials, the cooling strategies a longer mission would need still live mostly in laboratories and proposals, not on hardware waiting on a launch pad. Orbiters have gotten sharper every decade, but for anything happening at the surface itself, over hours, days, or weeks, we are still reading data a handful of Soviet landers gathered before most of today's mission planners were even born. So, the standoff sits exactly where it has sat for decades. The case for returning has never been stronger. A former ocean world, a working model of climate collapse, the only nearby comparison point for reading worlds we will never visit in person. The walls blocking the way back, the heat, the pressure, the chemistry, the cost, have not moved an inch. Mars, meanwhile, keeps collecting the funding and the attention that a strengthening case has still not managed to earn. That gap had very little to do with rocket science. Somewhere inside it waited a very different kind of explanation, one that had nothing to do with heat or pressure at all. It is worth asking why Mars, of all the competing destinations, became the one that always won the room. Not because the case against Venus grew weaker. The case, if anything, kept getting stronger. Something else decided the outcome, and it had almost nothing to do with physics. Mars feels like a place. Venus feels like a warning. That difference alone does more work in a funding hearing than most people would guess. Photographs from Mars land somewhere a listener can already picture. Dusty plains, rounded hills, scattered rocks under a pale butterscotch sky. Call it a cold desert, and the mind fills in the rest on its own. Red sand, frost at dawn, buried ice a few centimeters under a rover's wheels. Something a person could imagine walking across or building on. Venus offers none of that. Point a camera at Venus from orbit, and you get one thing: a smooth, yellowish-white blanket of cloud. The same from every angle, every week, every year. The actual ground sits behind roughly 90 kilometers of dense atmosphere, about the distance you might cover in an hour on an open highway, except instead of unrolling sideways in front of you, it stacks straight up over your head. The handful of true surface photographs that exist look less like a landscape and more like the inside of an industrial test chamber. Flat grey rock, hard shadows, no horizon worth walking toward. There are only a few of those images in existence, low resolution, taken decades apart, nothing for the imagination to build a place out of. Venus's story compresses to 3 words on repeat: crushing, scorching, acidic. A place you survive, not a place you explore. On vibe alone, Mars wins before anyone opens a spreadsheet. Mars hardware also lives long enough to tell a story with chapters. Launch. The tense final plunge through the atmosphere, engineers call it 7 minutes of terror. First images, first drives, first drill samples pulled from a Martian rock, then years of dust storms, strange formations, new craters, selfies beamed home from a machine still working long after anyone expected it to quit. A long-running series, one that keeps its audience and keeps justifying its own budget. Venus gives you a burst instead. Launch, cruise, entry, descent, touchdown, a rush of data. Then, within an hour or two, silence. One intense scene inside a very short film. There is no time to get attached. Often the lander is already dead before most people even hear that it landed. Long-range plans read, Moon to Mars. Build a foothold on the moon, use it to reach Mars, let each step set up the next. Venus cannot slot into that sentence. Pitch Moon to Mars to Venus's surface to a room of planners, and the sentence collapses on its own, because with today's physics and materials, a person standing on that ground would be crushed and cooked within seconds. Cloud City concepts, floating far above the worst of it, are worth taking seriously, and this piece will return to them. But they remain far future and high risk today, so Venus cannot borrow momentum from the one storyline. Humans are going to live there. That reliably moves budgets. Mars also built a brand, one success stacked on the next. Viking in the 1970s, Pathfinder and its small rover, Sojourner in the 1990s, Spirit and Opportunity in the 2000s, Curiosity in 2012, Perseverance and its small helicopter, Ingenuity more recently. Each landing taught engineers something the next mission could reuse. A heat shield refined, a landing method proven, a rover chassis improved. Each mission bought public interest bought funding, and funding bought the next mission. A loop that kept feeding itself, technically and emotionally at once. Venus had its own intense chapter. The Soviet landers, the flybys, the orbiters, and then long stretches of near silence. No long-lived rover, no dramatic stream of new images, no helicopter clips circulating online. The public filed Venus under sorted out decades ago, and at budget time Mars arrived with momentum behind it, while Venus arrived as a harder sell with a thinner emotional case. That popularity gap sounds harmless. It is not. Lean this heavily on one planet and you end up doing climate science, real climate science, on a sample size of one. In almost any other field, a model built from a single data point would be laughed out of the room. Somehow, for entire rocky worlds, Earth alone became the baseline. Mars became the cold, maybe habitable cousin, and Venus became the outlier nobody bothered to plot. Not a fair contest. A popularity contest, decided long before the data finished coming in. Venus is the other major rocky planet built to roughly our own size, sitting in our own neighborhood, and it took a completely different climate path than Earth did. That makes it the control experiment climate science actually needs, the one comparison that could show which parts of Earth's stability are dependable and which ones sit closer to an edge than anyone has confirmed. Without it, every model of a rocky planet's climate is built and tested against the same single case, over and over, with no second answer to check the first one against. Let Mars keep the spotlight, and that second data point simply never gets collected. So a real share of why we never went back has nothing to do with heat, or pressure, or chemistry at all. Everything that shapes a mission, story potential, public appetite, a plausible human roadmap, lined up behind the red planet and left Venus as the evil twin, studied politely from a distance and rarely up close. And yet one detail from that same story refuses to fully go quiet. The pool of a city standing in the one band of sky where Venus stops trying to kill you. There is one place on Venus that is not trying to kill you on temperature or pressure, and it sits nowhere near the ground. Rise past the fire and the crushing weight, and somewhere between 50 and 60 kilometers up, the numbers turn ordinary. Temperature in the range of roughly 20 to 70 degrees Celsius. Pressure close to 1 bar. Step outside and the air would still poison you in seconds. The carbon dioxide never lets up, but the crushing and the cooking finally stop. Inside a sealed habitat at that altitude, a body would not feel squeezed the way it would near the surface, and it would not need a hull built like a submarine's just to keep from being pressed flat on 2 of the 3 measurements that make the rest of Venus a death sentence. This one slice of sky reads almost calm. It is the reason concepts like NASA's Havoc exist at all. Sketches of crewed airships drifting at roughly 50 kilometers, exploring from above instead of digging in below, not a fantasy sketch drawn to look hopeful. The physics behind it actually checks out. Here's the part of the concept that costs nothing extra. Carbon dioxide is heavier than the nitrogen and oxygen mix that fills human lungs, roughly 78% nitrogen and 21% oxygen, the same mix any sealed habitat already has to carry for its crew. Fill a large envelope with that ordinary breathable air, and the envelope becomes lighter than the CO2 pressing in around it. It floats. Not an exotic lifting gas, not something shipped along for the ride. The habitat's own air does the lifting, the same way a blimp on Earth needs helium, or heated air pumped in specially. Except here, the thing keeping people alive doubles as the thing keeping the city up. That single fact is enough lift to hold platforms tens of meters across. Airship scale, not a child's balloon. And it is the closest thing this planet offers to a free engineering gift. No tanks of helium to launch from Earth. No separate lifting system to design, test, and keep pressurized on top of everything else. The air a crew breathes, and the structure that keeps them aloft turn out to be the same problem solved twice by the same solution. But a gift with strings attached is still a bill. That friendly band sits inside the sulfuric acid clouds, and the clouds do not pause for the one layer of sky that happens to feel comfortable. Droplets there may be more dilute than laboratory-grade acid, but they are still acid, and they hit the skin of a floating city minute after minute, year after year. Every cable, every joint, every solar panel and radiator and antenna sits inside a slow, continuous chemical attack. Wrap the whole structure in advanced composites, fluoropolymer coatings, corrosion-resistant metals, and the attack does not stop. It only slows. Even a protective shell an inch or 2 thick, thicker than most spacecraft skins ever need to be, has no track record against a decade of flexing, ultraviolet light, and acid working together. A hairline crack lets the acid in. A coating crazes and peels. A fiber quietly loses its strength. Nobody has the long-term data to say a material stack survives that combination for years, because nobody has ever left one up there long enough to find out. The habitat skin is not the only exposed surface either. Solar arrays sit outside, catching what filtered light makes it through the haze. External radiators sit outside, shedding heat the crew's own systems generate. Antennas sit outside, holding the only link back to an orbiter or to Earth. Every one of them needs the same acid resistance as the hull, and every one of them is harder to armor than a sealed wall, because each still has to do its actual job while surviving the chemistry trying to dissolve it. And the sky will not hold still long enough to make testing easy. That same altitude band sits inside Venus's super rotating winds, close to 100 meters a second, wrapping the whole planet in about 4 days. Drift freely, and a city circles Venus again and again, fine for measuring the atmosphere, useless for staying above one region, tracking a surface feature, or holding a steady link with an orbiter passing overhead. Staying in place inside a jet stream, that fast means constant propulsion, constant course correction, buoyancy adjusted on the fly, all of it burning power and adding parts that can fail. Navigation has to account for a platform that never stops moving relative to the ground below it or the spacecraft above it. And a communication link has to be re-aimed continuously rather than pointed once and left alone. Not a parked outpost. A moving target inside a fast-moving sky. Add it up, and the honest verdict is not dismissal, it is arithmetic. A narrow band of Venus offers real temperature, real pressure, and a lift mechanism that costs nothing extra to carry. Not a mirage on those 2 counts, but everything else, the acid, the wind, the years of unproven fatigue, stays as extreme as anywhere else on the planet. Building something that survives all of it at once means clearing a short list, and every item on it is still open. First, Materials tested for a decade in exactly this chemistry, not a lab sample exposed for a few weeks and called promising. Second, aerostats, the balloon and airship structures themselves, able to shrug off micro-leaks, self-patch or be repaired in flight, and hold their shape and buoyancy for years instead of months. Third, steady power. Sunlight already filtered thin by the very clouds doing the corroding, or a compact reactor carried along and kept safe from that same chemistry. Fourth, guidance and communication that keep working inside constant turbulence, with no repair crew within 100 million kilometers if any of it fails. Set beside a Venus cloud city, a base on the moon or on Mars looks almost easy by comparison. Solid ground under a structure, familiar metals and familiar polymers, the kind already flight-proven on other worlds. A blanket of loose surface material, regolith, that can be piled over a habitat for shielding without anyone inventing a new material class to do it. No requirement that the entire floor of a home also serve as the one thing standing between its occupants and a fall through 90 kilometers of poison air. That is why the sketches of airships over Venus have stayed sketches, caught somewhere between serious engineering and a good illustration, while landers keep rolling across Mars instead. And even without a single habitat ever built, that same friendly band keeps raising a different question, quieter than engineering. Something does not need a crew inside it to be interesting. It only needs to be capable of holding something alive. That capability does not answer whether anything is actually up there breathing it in. It only keeps the question open, and the only place worth asking it sits inside that same narrow slice of sky. 50 to 60 kilometers up, pressure near 1 bar, temperature close to a mild day back home. The same coordinates that make a floating city physically plausible also make this the one spot on Venus where biology as we understand it might survive. Some researchers have asked a stranger question than whether people could live there. They have asked whether something already does. Tiny acid droplets acting as private homes for microbes, running on sulfur chemistry instead of the oxygen-based kind behind every living thing on Earth. Not proof. A hypothesis with just enough physics behind it to survive being asked out loud. It is not a fringe idea dreamed up for its own sake. Earth has organisms that thrive in concentrated acid, in boiling vents, in clouds of their own choosing. So the droplets themselves are not automatically a deal breaker. Only the chemistry inside them is unfamiliar. Nobody claims to know that anything is living in that band. The claim is only that the temperature and pressure stop ruling it out, which on a planet this hostile counts as a real result on its own. That hypothesis eventually found itself a piece of evidence to argue over. A few years ago, researchers reported phosphine in Venus's clouds at levels measured in parts per billion. On Earth, phosphine shows up almost exclusively where biology is producing it. In swamps, in guts, in industrial byproducts, rarely anywhere else. So the natural question followed fast. Could a gas long treated as a signature of life on our own planet be turning up on another one? Other teams reprocessed the same data and found calibration problems, competing noise estimates, and non-biological chemical pathways that could, in principle, make the same molecule without a single living cell involved. New observations came in on both sides, some supporting the original detection, some failing to find it at all. Years later, the argument has not closed. Not a discovery, not a dead end either. A live disagreement that keeps a strange possibility technically on the table. That open question raises an old problem. Send a probe carrying Earth microbes into a place that might already host its own biology, and you risk manufacturing your own discovery. Find something odd in the clouds a decade from now, and the honest first question has to be whether Venus put it there or a dirty bolt on the lander did. Whether the mission found alien chemistry or simply found itself. So instruments still get cleaned and sterilized before launch, the same discipline applied to every world where the answer is not yet known. But Venus does not demand the caution Mars does. Even inside the mild band, sulfuric acid, ultraviolet light, and constant high winds make survival hard for a hitchhiking Earth microbe, and the surface below kills almost anything instantly. Mars, with ice and buried brines that could shelter a stowaway indefinitely for years, sits in a stricter planetary protection category. Venus sits in a looser one, a grey zone, licensed to be a little bolder with the hardware, paired with a standing obligation to stay skeptical about whatever that hardware finds. None of this has produced a stampede back to Venus, because next to the alternatives, one thin cloud layer is a modest bet. Mars offers subsurface ice, salty brines, maybe buried aquifers, several separate places water might still sit today. Europa and Enceladus almost certainly hide entire oceans of liquid water under their ice, stable, deep, chemically rich reservoirs. Venus offers a single band, only 10 to 20 kilometers thick, thinner than the distance from a city centre out to its farthest suburbs. Everywhere outside that band, the planet is too hot, too dry, or too acidic, and the ground below sits sterile under conditions already established. Hot enough to melt lead, crushing enough to feel like standing under hundreds of meters of ocean. Given a limited budget and a mandate to look for life, Mars and the icy moons offer many doors. Venus offers one, and it stays propped open only by an argument nobody has finished having. But the clouds were never where the biggest opportunity was hiding. If Venus once carried oceans, then billions of years ago, some version of this planet may have looked as promising as early Earth. Warm water, moderate temperatures, sunlight in steady supply. Anything that lived then would not have left its record floating in the atmosphere. It would have left it in rock. And the rock is the problem. Venus appears to have been resurfaced by enormous volcanic flows, lava hundreds of meters thick in places, deep enough to bury a 40-story building and leave nothing showing above the rubble. Whatever older terrain sat beneath that lava, oceans, shorelines, anything a former biosphere might have written into the stone is very likely still down there. Not gone, buried, sealed under rock, hot enough to alter whatever it covers. Reaching it means drilling into that same ground, with the same heat, the same crushing pressure, the same corrosive air, and the same hour-long clock that has ended every lander so far. Confirming that Venus once carried life, and then lost it, would do something no other discovery in the solar system could. It would prove that Earth-like is not a permanent label, that a planet the right size, at the right distance, with the right ingredients, can still slide from ocean world to furnace and never come back, and that this is a real path a planet can take, not a rare freak accident. We tend to assume a world in the right size range, at the right distance from its star, stays habitable more or less by default. Venus would put a warning sign on that assumption. It would force a rewrite of how confidently anyone reads a distant, Earth-sized planet as safely habitable, including the ones astronomers are finding right now around other stars. It is exactly the kind of find that should send missions racing back with better instruments, tougher landers, and dedicated cloud probes. The barriers stopping that race are the same ones that have kept every mission grounded for 40 years. Some of those barriers, though, are not permanent. If the planet keeps telling us to come back stronger, it is worth asking what stronger would actually mean, and how close we actually are. The honest answer is uncomfortable in a useful way. The thing keeping us off Venus right now may not be physics at all. It may be hardware stuck in the 1980s. The planet has not changed since the Venera era. Our tools finally might be catching up. Start with the part that changes the most. Electronics. Today, a mission babies its chips under roughly 120 to 150 degrees Celsius, and everything past that number is borrowed time on a countdown. But full computer systems built from silicon carbide or gallium nitride, wide bandgap materials that behave completely differently under heat, could run at something like 500 degrees Celsius, close to 930 degrees Fahrenheit. No giant insulated cooler, no short-lived cold capsule racing a clock, just circuit boards bolted straight into a pressure vessel, sitting in air past 460 degrees and staying fine. Labs have already run simple silicon carbide logic circuits, amplifiers and sensors at Venus-like temperatures for thousands of hours without failing. The next step is harder. Scaling that up into a complete avionics suite, processors, memory, communications, power control, all built in these wide bandgap materials and packaged to survive heat and pressure together. If that scaling succeeds, the whole mission profile flips. Not 90 minutes and then everything cooks. Days, maybe weeks. electronics that are no longer standing on a countdown timer. Chips that survive are only half the problem. They still need a body around them that survives the same heat, the same pressure, and the same acid, which is where advanced materials come in. Picture a lander shell built as a stack of purpose-built layers rather than one thick slab of metal. An outer layer of ceramic or coated alloy to resist sulfuric acid and hot carbon dioxide. Beneath that, a layer engineered specifically to take 90 plus bar of mechanical stress without cracking. Beneath that, a thermal barrier layer slowing the heat's march inward toward the electronics. Altogether, several centimeters of engineered armor, roughly an inch or more, doing the work that used to require one heavy, compromising wall. Metamaterials and tailored microstructures could push this further still. Surfaces engineered to reflect infrared heat efficiently while resisting corrosion at the same time. The goal is not heroics, the goal is routine. Designing a Venus-rated shell the way a deep-sea submarine hull is designed today. Tough, expensive, standard, better electronics and better armor solve the survival problem for one machine. But there is a smarter question underneath it. What if you stop trying to make one machine survive at all? Rather than build a single flagship lander that must do everything and live forever. A newer line of thinking accepts that Venus kills hardware fast and simply uses that fact. Swarms of small probes, dozens, maybe hundreds, of cheap, rugged descent capsules, each expected to last somewhere between 10 minutes and an hour. They do not roll, they do not drive, they fall, they land, and they stream whatever data they can gather back to an orbiter while they still have time. Some tuned to near-surface temperature and wind, others to chemistry, others to seismology, listening for the shiver of a distant quake. A single launch could scatter these probes across different latitudes, longitudes, and altitudes, and a relay spacecraft overhead stitches the fragments together into something no single lander could ever produce. A picture of how temperature, pressure, and chemistry actually vary from place to place, how the near-surface air behaves at different times, how often the ground trembles or a vent stirs. Each probe alone is expendable. Together, they become a statistical, time-resolved snapshot of a planet that has only ever offered single, isolated glimpses. There is a third path, and it does not choose between the sky and the ground at all. Hybrid platforms that dip and rise. A buoyant craft spends most of its time floating in the cooler, more manageable band around 50 to 60 kilometers up, where temperature and pressure sit close to a mild day back home. Then, on command, it increases its density or fires a small rocket and dives toward the surface. It runs its instruments for a few minutes in direct contact with the rocks and the crushing air below, gathering exactly the kind of ground truth no orbiter can offer. Then it rises again, climbing back into the cooler layer before the heat fully saturates its systems. Each dive lasts only minutes, but repeat that dive dozens of times over days, sampling different terrain, different times of the Venusian day, and the mission stops being a single all-or-nothing gamble. The planet becomes a test bed you dip into, again and again, rather than a door you get to open exactly once. All four ideas point the same direction, and none of them are science fiction. The picture did not hold. On paper, hot electronics, layered armor, probe swarms, and hybrid platforms could break the deadlock that has held since the Venera era. In practice, every one of them is expensive to build before it is ever expensive to fly. Turning silicon carbide and gallium nitride from lab demonstrations into fully space-qualified computers costs real money and real years. Building and testing centimeter-thick, multi-layer shells under true Venus conditions, real heat, real pressure, real corrosive gas at once, needs specialized facilities that do not exist on every campus or contractor floor. Flying a swarm or a hybrid platform needs entirely new mission architectures, new software, new ways of assessing risk that current review boards have not fully built yet. None of this happens on the side of a normal program, squeezed in between other priorities. It needs a dedicated push, a flagship Venus mission, a sustained technology initiative, an international campaign willing to share the cost and the risk. Without that kind of commitment, progress creeps forward in small pieces, A test circuit published in a journal here, a materials paper there, a small tech demonstration riding along on someone else's mission, never at the scale it would take to actually land something new and tough on the surface. The tools are visibly on the horizon. Not a small preference. The deciding factor, again, the same one that has decided almost everything else about Venus. The financial engine has not switched on. That gap between what the technology could do and what has actually been funded is where the next question has to live. What exactly has made it onto a real mission manifest? The honest answer is a return already underway, quiet and careful, 3 approved missions circling back to Venus for the first time in a generation. None of them touch the ground and plan to stay there. All 3 fly above the atmosphere or fall through it once, on purpose, keeping their distance from the one place that has always defeated us. NASA's DAVINCI comes closest to an actual landing. Deep atmosphere. Venus investigation of noble gases, chemistry and imaging drops a probe straight down through the sky, reading pressure, temperature, wind, and the exact chemical makeup of the air the whole way down. Its real prize is noble gases and isotopic ratios, especially the same deuterium to hydrogen balance that first hinted at Venus's vanished oceans. Those ratios carry the planet's climate history the way rings carry a tree's age. DAVINCI is not built to last long once it touches down. Most of the science happens on the way. A vertical slice from the cooler upper air into the crushing lower atmosphere. A few minutes of surface data would be a bonus, nothing more. The fall itself is the experiment. A second mission looks down instead of through. VERITAS, Venus emissivity, radio science, INSAR, topography, and spectroscopy exist to fix a map that has not been touched since the early 1990s. Magellan gave the world a global radar picture of Venus at resolutions down to a few hundred meters, useful in its day, but blurry by current standards. VERITAS resolves surface detail down to tens of meters, roughly the length of a single city block, a leap from a blurry radar globe to a genuine geologic map. That kind of resolution lets scientists trace fracture zones, volcanic vents, and the youngest lava flows, and measure surface emissivity and gravity for clues about rock type and what moves underneath the crust. A third mission, Europe's EnVision, carries its own radar and adds something Magellan and VERITAS cannot offer on their own. A look beneath the surface. Subsurface sounding hunts for buried structures, shifting magma, and signs that a volcano erupted recently rather than a billion years ago. Put the 3 together and a coordinated attack takes shape. DAVINCI reads the atmosphere for what it says about lost oceans and climate history. VERITAS and EnVision read the solid planet for how it behaves right now, how fast it resurfaces, where heat still escapes, whether volcanoes are erupting somewhere on Venus today. Together they aim at the same 2 questions that have shadowed this whole planet from the beginning. Is Venus geologically alive? And how did a world that may once have looked like Earth end up looking like this one? Here is the honest limit of all 3. Every one of them is an orbiter or a single pass through the sky, not a lander, not a machine that survives, adapts, and keeps reporting back season after season. A probe that falls once and goes dark is not the same thing as a platform that watches a planet change over months or years. That gap has not closed. No fully approved next-generation lander built around silicon carbide electronics and the layered armor described a moment ago sits on any agency's actual manifest. Only concepts, only proposals, only a folder of very promising paperwork still waiting for a budget line. That absence matters more than it might sound like it should. Orbiters and single-pass probes can describe a planet from a careful distance. They cannot watch one live. Catching an eruption in the act, tracking how surface chemistry shifts across a long Venusian day, feeling for the small tremors that would confirm the ground is still active, all of that needs a sensor that stays put and keeps working. Even a generous reading of the current lineup gives Venus a set of snapshots, not a witness. Expect a staggered trickle of results through the rest of this decade and into the next. Atmospheric profiles from DAVINCI's Fall, sharper maps from VERITAS, fresh geophysics from EnVision, layer by layer, Real progress and worth the decades-long wait. A true return to the surface, one that lasts longer than an hour and keeps sending data back, still sits somewhere past that timeline, tied to the same mix of high-temperature electronics, tough materials, and sustained funding this whole story keeps circling back to. Venus, right now, sits in a strange in-between state. No longer ignored, not yet confronted. Approached sideways, carefully, from just above the kill zone, waiting on the mix of technology and will it would take to finally go the rest of the way down. That mix, technology on one side, will on the other, is really the whole story compressed into a single sentence. Take it apart, piece by piece, and the answer to the original question stops being complicated. Every part of Venus is hostile to the machines we actually build. The surface sits near 460 degrees Celsius, held there permanently by an atmosphere pressing down with something like 90 times the weight of Earth's air at sea level. That air is mostly carbon dioxide laced with sulfur compounds, chemically active at every altitude. And underneath all of it sits the plainest limit of all. Ordinary silicon electronics, the kind that runs almost every spacecraft ever flown, stops behaving like a computer long before the thermometer gets anywhere near that number. The early Soviet landers did not fail. They worked. Each one touched down, gathered what it could, and died exactly on schedule. Minutes for the first successful landing. A little over 2 hours for the best of them. Every instrument aboard those capsules was well engineered for its era. Tested, shielded, built by people who understood exactly what they were sending it into. And still, the planet won every single time, on a fixed and predictable clock. That is not a broken mission. That is a confirmed result, repeated enough times across enough attempts to stop being an accident. 20th century hardware, however well built, cannot hold a foothold on that surface. Not a flaw in the engineering, a flaw in the premise of using that generation of hardware at all. So, the decision that followed made a certain kind of sense. Point the money, the launches, and the best engineering minds at worlds that behave more predictably. The Moon, Mars, the icy moons further out. Places where machines can be trusted to keep working past the first hour. Where a rover can wake up the next morning and try again. That choice built real decades of real science, and none of it was wasted. It also carried a cost nobody put on the ledger at the time. Turning away from Venus meant turning away from the most extreme and arguably the most relevant climate result sitting anywhere in the solar system. Venus stopped being a planet we studied and became a slide, a scary example dropped into a presentation to make a point, rather than a world anyone still seriously interrogated. A cautionary line in someone else's talk, not a live research target of its own. Here is the part that makes that retreat harder to defend the longer you sit with it. Venus is not some outlier world built from strange material under strange rules. Its radius sits close enough to Earth's, about 6,052 kilometers against Earth's 6,371, to look like a sibling from orbit. Its mass runs to roughly 81% of Earth's. Its surface gravity sits near 9/10 of what a body feels standing here. Same rock, same basic elements, same star. What differs is distance from that star, the makeup of the air, and above all, climate history. One planet ended up with oceans, a working carbon cycle, and eventually life looking up at its own sky. The other ended up with skies of carbon dioxide, clouds of sulfuric acid, and a surface hot enough to melt lead. Not a coincidence of geology, a branch point. And the branch point is exactly why Venus matters, because understanding how one near twin locked into that ending is the clearest way to understand how stable the other twin's comfortable state actually is. None of this argues for colonizing Venus, and it never did. Nobody serious is proposing domes on that surface, or cities among the acid clouds, as a near-term goal. That version of the story, the one with footprints and flags, was always going to belong to somewhere else. What the case actually calls for is data, continuous measurements of the atmosphere and the ground over time, not a single frozen snapshot from a lander that dies within the hour. A clear answer on whether the planet is still volcanically active right now, tighter numbers on how much water it once carried, and how quickly that water disappeared. A direct instrument reading on the clouds themselves, settling the phosphine question instead of another round of arguing over a faint signal from orbit. And eventually, a lander built to survive long enough to watch the ground and the air act on each other in real time instead of guessing from a single frozen moment. The prize at the end of that work is not a colony. It is the ability to look at a newly found, Earth-sized planet circling some other star and say, with real confidence, that one probably kept its oceans, or that one probably went the other way. And the return on that investment would not stop at Venus. Electronics built from silicon carbide and gallium nitride, the two materials able to hold together above 500 degrees without a cooling system, could ride along on probes dropped into the atmospheres of the outer gas giants, or sit inside industrial equipment on Earth that runs far hotter than anything built today can tolerate. Shells layered to shrug off acid and heat at once could protect hardware near any other furnace world, or inside a fusion or fission system built here at home. Swarms of short-lived, expendable probes, or platforms that dive and rise instead of gambling everything on one landing, could work just as well over Titan or any thick atmosphere world found around another star. None of that work has to wait for a Venus mission to justify it. Every gain shows up somewhere else first, in an industrial furnace, in a probe headed for a different planet entirely, long before it ever gets bolted into a Venus-rated shell. Sol Venus and an entire category of no-go environments quietly opens. The solar system stops being a set of postcards taken from a safe distance and starts being a working set of experiments. One cold, thin-air desert, one living ocean world, one runaway greenhouse, each one explaining by contrast why the others turned out the way they did, which leaves the real answer, the one underneath the technical one. We did not stay away from Venus because it was simply too hard. Plenty of hard problems get funded when the story around them is good enough. We stayed away because that planet frightened our hardware on contact and never fit the version of the future we liked telling, rockets landing softly on dusty ground, footprints, a base, a flag. Venus never offered any of that, and so it slid out of the conversation. But a planet that shows exactly how an Earth-like world can fail is not a side detail. It may be the single most useful warning sitting in our own solar system, and once it is understood that way, looking away from it stops being a neutral choice. We walked away from the one nearby world built almost exactly like ours, right at the moment we most needed to hear what it had to say. Every telescope, now finding another Earth-sized planet around another star, is quietly asking the same question Venus has been sitting on the whole time, whether that new world kept its oceans or lost them for good. What is left now is a plain question, still open. Whether the tools finally get built to go back on our own terms, patient, well-armored, built for the heat instead of merely surviving it, or whether the lesson sitting under a sky that presses down with 90 times our own weight of air, wrapped in acid and carbon dioxide, keeps getting treated as somebody else's problem to solve another day,